Good morning, everyone. We will be presenting the spray pyrolysis for the synthesis of nano-high-temperature ceramic powders. My name is Juan Estepa, and these are my partners, Mehta and Reyes, and our advisor is Dr. Chang. We have separated our presentation into different sections. We're going to start with what we're going to do. We're going to explain the process in which we're going to do it and how we're going to achieve these goals. Okay, we're going to design and optimize an in-house spray pyrolysis system to synthesize high-temperature nano-ceramic powders. We're going to adjust for a variety of materials that range from the more conventional metal oxides to the more challenging metal carbides. Our motivation and goals. We're creating a system that will result in smaller, finer particle sizes and that is continuous and scalable. Also a system that will optimize product yield. Why use spray pyrolysis? We're using spray pyrolysis because it is an economical system that is also versatile. You can use it with different substances to achieve your goals. Also, it has the added bonus that you can operate it at an ambient pressure. There are three basic steps to spray pyrolysis. First, it's the generation of droplets from a precursor solution. And then once in a furnace, the droplets will shrink due to evaporation. And finally, it will go under a chemical reaction that will convert the precursor solution into the desired solid ceramic powder. Precursor solutions. There's two basic types of precursor solutions that are used. One is an emulsion, which is a colloidal dispersion of two different liquids, and a sol, which is a colloidal dispersion of a liquid with solid particles. Aqueous solutions are the most common precursor solution used in spray pyrolysis due to the fact that it's economical, they're easy to handle, they're safe, and they are readily available. For the atomization of the precursor solution, there's three basic techniques used, starting with the pneumatic atomizer, which uses a high pressure, high velocity air to separate the particles. Next, the ultrasonic atomizer, which uses high frequency ultrasonic sound waves. And lastly, the electrostatic atomizer, which uses a high voltage electric current that separates the droplets. And these three atomizers affect the droplets in different ways. Including the size, the velocity of the droplets, and the rate of atomization. In this project, our target goal is to atomize a large quantity of droplets, small droplets, at a low exit velocity. To continue, I present Reyes.
Droplet size is an important parameter as it determines the heating rate and the residence time. It is ideal to obtain small particles, as it is said that the smaller the particle, the better the mechanical properties. The droplet characteristics depend on density, viscosity, and surface tension of the precursor solution. In a past experiment, 3 atomizing techniques were tested in order to define whether there was a relationship between the precursor droplets and the powder particles. As it can be observed, the ultrasound modulated 2-fluid atomizer had the best results. It produces a high throughput and a low drop size distribution. This shows that we can obtain a controllable and effective system. In addition, the UMTF atomizer produced the smallest particles out of the 3, which defines the initial parameters for the atomizer, as well as it proves that there is a relationship between the initial droplets and the resulting particles. These 2 equations represent a way in which we can obtain theoretical values for the droplet diameter, which will serve as a comparable measure when we test our system. There were other parameters that kept showing up through our research. One of them is frequency, which is recommended to be set around 20 kilohertz and 2.5 megahertz. The other one is temperature, which is recommended to be set around 1400 degrees Celsius for carbide metals. We were able to find one precedent which synthesized spherical beta carbide particles. The precursor solution contained colloidal silica, saccharose, and boric acid. The carrier gas was argon, which was flowing at a rate of 1 liter per minute. The frequency of the atomizer was set to 2.5 megahertz, and the temperature of the furnace was 900 degrees Celsius. The results show a discrepancy when compared to the theoretical values, and this is because in reality, sometimes droplets come together to form a particle, which differs from the initial assumption that one droplet makes one particle. In conclusion, these results also show that spray pyrolysis can be used to synthesize non-oxide metals. However, our goal will be to obtain particles that are less than 1 micron in size. We collected several related standards from the International Organization for Standardization, as well as the American section of the International Association for Testing of Materials, which will serve as a reference as our project progresses. We also took into account how our project will have a global impact. We concluded that our project furthers research in a rather novel topic, as well as improves application in the aerospace, energy, and defense industries. While improving these industries, we are contributing to the economy, the environment, as well as advocating for collaborative research. Now, continuing, Mehta.
So we have some constraints in this design. Some of them are gravity, temperature, and the available space. Gravity, because as soon as the droplets enter the furnace, they tend to drop to the bottom of the furnace before reaching the end of the furnace. Temperature, because to synthesize carbide particles, we need high temperatures, and that would cause stress on the furnace and may lead to cracks. Also, since this is a lab equipment, we have a certain amount of space to set up the system. So, for a design overview, the system will have a precursor solution, which will be pumped into an atomizer. Once the atomizer inserts the droplets into the furnace, they will go through the furnace under a chemical reaction and will be collected in a collection chamber at the end. A major component is dealing with gravity, which we can control using changing the type of carrier gas or the chemistry of the original precursor solution. So for the first design, we are considering using a continuous low flow pump and a high temperature nozzle. You can see the flow rate of the pump. It can be configured to have 1 or 2 syringes. Also, the nozzle has a temperature rating of 600 degrees Celsius and it's made of titanium. For the second design, we're considering using a variable speed peristaltic tubing pump, which has a cost of about $500. It also comes with a European outlet adapter, so that's a little global design there. It has a flow rate range of 0.005 to 600 milliliters per minute. The second part of this design is a gravity component. We're considering using a fan, so it could assist in getting the powder particle from one side to the other side with less material loss, which means like less falling on the furnace due to gravity. Overall, we plan, once we have a pump and atomizer selected, we will design the entire system, like the pipings and all that. And this is the timeline for our project. By next semester, we plan to do the testing and optimizing the system and seeing if it works for carbides. Overall, we need to purchase the components like the pump and the atomizer and manufacture as needed. Then once we have the pump and the atomizer selected, we need to select a cooling mechanism and a collecting mechanism for the powder. So once we have that, we will test and optimize the system, and that would be our final design. Thank you. Any questions?
What do you do with this ceramic stuff when you're done with it? What's the ultimate, you never said what the ultimate use of the ceramics are. Is it widespread?
Yes, there's a lot of industries that it can be used in, including like aerospace and energy applications. Basically, the ceramic powders can withstand higher temperatures than what's available at the moment. So they could improve, for example, like aerospace vehicle re-entering the atmosphere, being able to handle those temperatures with a better capacity.
This is our zirconium carbide, which is our ultimate goal. It has a melting point of 2,750 degrees Celsius, so it's really strong in that terms. So in terms of aerospace,
How about coating? Like I use inserts to machine, and we use coated, coated carbides, and they coat it with ceramics.
Yeah.
Yeah.
Is that the kind of
So
stuff?
application.
Yeah.
Okay.
And so we are trying to make smaller particles, which will give those applications better mechanical properties. You know, they will improve strength, and so it makes them better.
Smaller than.
Yeah.
Sir?
Okay. You said your desired size was 0.44 microns?
That was one of the desired size of one of the research papers we found. Their desired size for beta silicon carbide particles was 0.44, which they came up with from the equations we had, Lang's equation. So.
But
for
your
that-
target is 1 micron?
That's the-
Yeah, our
Under 1
target
micron.
is to have under 1 micron.
the
So
smaller-
why are you calling it not nano-ceramic powders?
Well, it said that like it's considered nano if it's less than 1 micron.
Oh,
In
the,
yeah.
yeah. Or end goal. Yeah. Sorry.
That's our goal.
Yeah.
Under 1 micron is
Under
our
1
goal.
micron is our.
Which
Is
is
your
what we're
goal.
getting from other experiments. We're trying to match and do it with the zirconium carbide, which hasn't really been researched into before.
It's been more like oxides in
Oxide
terms
metal.
of research. So carbides are, we've been only able to find one paper like, which make powder from carbides. So like some people did coatings with zirconium, but since we're looking for powder and carbide.
Okay.
So,
Second question I have to ask you is, in your concept, you're using a fan to create a phenomenon called gravity. Why aren't you turning the furnace on its side and using gravity to drive the system?
We had definitely considered doing that. Due to the equipment that we have here on campus, we can't really adjust and create a new structure with the furnace that we have available.
it's a
Our
horizontal
furnace is
furnace.
horizontal.
That's another constraint.
Yeah.
We have the furnace.
It's a challenge.
Yeah. You
That's
can't
an-
like flip
I
it.
think
and
that's an easy challenge,
burn the
to be honest with you. The third, and then my last question. You showed that your best result was a 2-fluid atomizer system,
In the
and you're
experiment.
presenting here a 1-fluid atomizer system? Why?
We're still, the atomizer selection, we haven't finalized that yet. We've just considered one, we're still looking into atomizers. And the chemical solution, we are also in the process of doing CFD analysis and seeing like how the results come up, and then we can work on the solution itself, the precursor solution. So the chemistry behind that, we're still working on the chemistry of the precursor.
Okay, thank you.
Okay, thank you.
Thank you.
Thank you.
Can I make one comment? Sabri? Can I
Yeah, of
make
course,
one
please, go ahead.
Sorry, Laura, I have to make some comment. Anything less than 1 micron is not nanometer. It is 100 nanometers, so make sure of that
Right,
correction,
yes.
okay?
Yes.
If you are making less than 100 nanometer powder, then only it's considered nano, otherwise it's not nano, okay? Otherwise, anything between 100 nanometer and 1 micron is sub-micron, okay? So the goal of this project, as far as I know, is making powder under 100 below 100 nanometer.
Yes.
Okay, so it's not 1 micron. Let's make that one correction. Second thing, why nano?
Okay,
Our goal is to improve the mechanical properties of the powders already existing. So right now, since there's almost no research on carbide, there's other research on oxides where they have been able to make the nano particles. So we want to, make this system more versatile and be able to produce these nanoparticles for carbide metals.
I understand that, but why nano why you think nano will have better mechanical properties? That's my question.
Because when the particles are smaller, they're able to come together better. So when they are, it's like sort of when you're putting together smaller pieces, they combine better when they react in like the higher temperature.
Also, it can create a more even coating. For example, like when you're when you apply it to certain materials to withstand higher temperatures. So that the smaller material, it's less material, it's also more economical in that way.
Or uniformity.
Uniformity.
Yeah, uniformity.
Uniformity.
Okay, I'll stop there, look at your 3365 course. Okay, this is not the answer. Okay,
Thank you very much.
thank you.